Right now, as you read these words, a dead star 7,000 light years away is sending you a signal. It has been sending that same signal for longer than human civilization has existed. Every 1.3373 seconds, not approximately, not roughly, but with a precision that rivals the finest atomic clocks ever constructed by humanity, this cosmic lighthouse sweeps its beam across our planet. And it has never missed a beat. Not once in millions of years. We thought we understood the timing. We built pendulum clocks and celebrated their accuracy. We engineered quartz oscillators and marveled at their stability. We constructed atomic clocks that lose only 1 second every 100 million years, and we declared ourselves masters of precision. But the universe had already perfected this art billions of years before our solar system even formed. What we discovered spinning in the darkness of space humbled every clockmaker who ever lived. These objects, pulsars, rotate with such unfathomable regularity that when astronomers first detected their signals in 1967, the only reasonable explanation seemed to be intelligent extraterrestrial life. The researchers half-jokingly labeled the source LGM-1, little green men, because nothing natural, nothing born from the chaos of stellar explosions and gravitational collapse could possibly maintain such metronomic perfection. Nature doesn't work that way, except it does. It absolutely does. The numbers shatter comprehension. Some pulsars complete over 700 rotations every single second. That's faster than a kitchen blender. That's faster than the highest frequency sound you can hear. And yet, despite spinning at these impossible velocities, these objects maintain timing stability that atomic physicists openly envy. Millisecond pulsars deviate from their predicted signals by less than 1 microsecond over an entire decade. Your smartwatch would be ashamed of itself. Dr. Jocelyn Bell Bernal, the graduate student who first spotted these strange pulses on paper chart recordings, initially thought her equipment was malfunctioning. The signal was too clean, too regular, too impossibly perfect for the messy universe she knew. But the signal kept coming, night after night, week after week, from the same patch of sky. Either Cambridge had the galaxy's most consistent equipment failure, or the cosmos contained something nobody had ever imagined. What you are about to discover will fundamentally reshape how you understand precision, time, and the physics of extreme matter. We will journey into the hearts of objects so dense that a teaspoon of their material weighs 6 billion tons more than every car, truck, and airplane on Earth combined. We will witness magnetic fields trillions of times stronger than anything humans have ever created. We will see how death becomes a new form of existence, how destruction breeds perfection, and how the universe's most violent events create its most reliable clocks. But here's what makes this truly remarkable. These cosmic timekeepers aren't just scientific curiosities. They have already proven Einstein's general relativity with unprecedented precision. They have detected gravitational waves before any Earth-based detector existed. They may one day guide spacecraft across interstellar distances when GPS satellites are nothing but ancient history. The dead are helping the living navigate the future. If you're fascinated by the universe's hidden engineering, subscribe and hit that thumbs up. And here's something to ponder. What do you think is the fastest spinning object ever discovered? Drop your guess in the comments below. I'll pin the most creative answer, and by the end of this video, you'll know exactly how close you came. Throughout this exploration, we will encounter 3 revelations that most people, including many who consider themselves science enthusiasts, have never confronted. First, we will learn why pulsars shouldn't exist at all according to the physics we teach in undergraduate classrooms. Second, we will discover how these objects have already revolutionized fundamental physics in ways that textbooks are still catching up to. And third, we will confront a philosophical puzzle that these cosmic lighthouses pose about the nature of persistence, identity, and time itself. This isn't merely a story about spinning neutron stars. This is a story about what the universe can accomplish when extreme conditions push matter beyond every limit we thought existed. It's about how chaos breeds order, how violence breeds stability, and how the cosmos builds clocks that will still be ticking long after every human achievement has turned to dust. The answers lie in quantum mechanics, gravitational physics, and electromagnetism converging in ways our equations barely accommodate. They lie in conditions so extreme that our vocabulary struggles to describe them. They lie in one of the most profound demonstrations that the universe operates with, mathematical precision even in its most apocalyptic moments. Now, let us begin with the most fundamental question. What exactly creates a cosmic clock capable of keeping time for billions of years? Chapter 1. Stellar Remains. Before we can understand why pulsars flash with such extraordinary regularity, we must confront the violent births that create them. Every pulsar spinning in the galaxy tonight was once something completely different, an ordinary star not so unlike our Sun, living a quiet nuclear existence, completely unaware of the transformation awaiting it. Stars spend most of their lives in a delicate balance. Gravity pulls inward, relentlessly trying to collapse the stellar material into the smallest possible space. Meanwhile, nuclear fusion in the core generates outward pressure, radiation pushing back against gravity's crush. For millions or billions of years, these forces achieve equilibrium. The star neither expands nor contracts. It simply exists, burning hydrogen into helium, then helium into carbon, then carbon into progressively heavier elements, all while maintaining this gravitational standoff. But this balance cannot last forever. Eventually, the fuel runs out. What happens next depends entirely on the star's mass. Smaller stars like our Sun will gently shed their outer layers, leaving behind a white dwarf, a dense ember roughly the size of Earth, slowly cooling over trillions of years. These are serene deaths, quiet endings. But more massive stars, those with at least 8 times our Sun's mass, face a far more dramatic finale. When a massive star exhausts the nuclear fuel in its core, the outward pressure that sustained it for millions of years suddenly vanishes. In less than a second, gravity wins. The core collapses at velocities approaching a quarter of the speed of light. Picture a mass greater than our entire Sun, compressing from something the size of Earth down to something roughly the size of Manhattan. This happens in approximately 10 milliseconds. The numbers stagger comprehension. Dr. Adam Burrows at Princeton University has spent decades modeling these collapses through supercomputer simulations. His calculations reveal that the collapsing core reaches densities exceeding 100 trillion times the density of water. At these conditions, electrons are squeezed directly into protons, combining through a process called inverse beta decay to form neutrons. The core becomes, quite literally, a neutron star, an object composed almost entirely of neutrons packed as tightly as the laws of physics permit. To grasp this density, consider a sugar cube of neutron star material. That tiny cube would weigh roughly 1 billion tons. If you placed it on Earth's surface, it would immediately begin falling toward the planet's center, punching through rock and mantle like they weren't there. Nothing we have ever encountered approaches this concentration of mass. Meanwhile, the outer layers of the dying star are still falling inward. They slam into the newly formed neutron star's surface and bounce violently. This bounce, enhanced by neutrinos streaming out from the core, blasts the star apart in a supernova explosion. For a few brief weeks, this single dying star can outshine an entire galaxy of 400 billion suns. The Crab Nebula, visible tonight with a modest backyard telescope, represents the scattered remains of exactly such an explosion. Chinese astronomers recorded the event in 1054 CE, noting a guest star so bright it remained visible during daylight for nearly a month. What they witnessed was a star's death scream, and what remained afterward was the pulsar still spinning at the nebula's center, still flashing 30 times every second. nearly 1,000 years later. Here's where the physics becomes truly extraordinary. During this gravitational collapse, two crucial things happen that will eventually produce the pulsar's precision. First, angular momentum must be conserved. Think of a figure skater pulling their arms inward during a spin. They rotate faster because the same rotational energy now occupies a smaller radius. A star collapsing from millions of kilometers to roughly 20 kilometers experiences the same effect, but amplified beyond imagination. The mathematics reveals why. If a star originally rotated once per month, typical for massive stars, and then collapsed to neutron star dimensions, conservation of angular momentum demands it spin roughly 1,000 times per second. The same rotational energy that once produced a leisurely stellar rotation now drives a neutron star spinning faster than a jet turbine. Second, the star's magnetic field gets compressed along with its matter. Magnetic field strength increases with the square of the compression factor. Compress a star to 100,000th its original radius, and its magnetic field intensifies by 10 billion times. Where the original star might have possessed a magnetic field comparable to Earth's, the resulting neutron star wields a field reaching trillions of Gauss strong enough to distort electron orbitals, strong enough to make normal matter impossible. Dr. Victoria Caspi at McGill University, one of the world's foremost pulsar researchers, has noted that these magnetic fields exceed anything achievable in terrestrial laboratories by factors of millions. We cannot recreate these conditions. We can only observe them from afar and attempt to model their behavior. What emerges from this apocalypse is something entirely new. Not a star in any traditional sense. No nuclear burning occurs in the core. Yet not dead either, because it still produces energy, still broadcasts signals across the galaxy, still interacts with its environment. A neutron star is stellar matter in an entirely novel phase of existence, following physical laws that only apply at these extreme densities. The newly born neutron star is incredibly hot, temperatures exceeding 100 billion degrees, hotter than the core of any normal star. It cools rapidly through neutrino emission, dropping to merely 1,000,000 degrees within a few thousand years. Its surface, if you could somehow stand upon it, you absolutely could not, would consist of an iron crystal lattice, possibly topped by an atmosphere mere centimeters thick, composed of ultra-compressed hydrogen and helium. And from the first moment of its existence, this object begins to spin, rapidly, precisely, tirelessly. The fundamental reason for this precision lies in what survives the collapse. The neutron star inherits and intensifies properties the parent star possessed but expressed only weakly. The slight rotation becomes furious spinning. The modest magnetic field becomes an overwhelming electromagnetic dynamo. And these properties, once established, become incredibly stable. Neutron stars have no internal combustion, no convection currents, no surface weather. They are solid, crystalline, and structurally rigid, more resistant to deformation than any material humans have ever imagined. This rigidity will prove essential to understanding their timing precision. But before we examine why they tick so perfectly, we must first understand what they actually produce, how their spinning creates the beams that sweep across our telescopes. The mechanism waiting to be revealed challenges intuition at every step. Chapter 2. Lighthouse effect. A spinning neutron star alone would be invisible to us. A sphere of compressed matter 20 kilometers across, located thousands of light years away, emits nothing our instruments could detect without extraordinary luck. What transforms these objects into the pulsars we observe is the marriage of their rotation with their magnetic field, a cosmic lighthouse mechanism that broadcasts precise signals across interstellar distances. Imagine you could witness this process directly. You would see a sphere spinning so rapidly it appears blurred, completing perhaps dozens of rotations every second. This sphere possesses a magnetic field, but here's the critical detail. The magnetic axis almost never aligns perfectly with the rotation axis. Just as Earth's magnetic poles differ from its geographic poles, a neutron star's magnetic poles sit at angles to its spin axis. Sometimes these angles are modest. Sometimes they exceed 90 degrees. This misalignment creates everything we observe. Charged particles near the neutron star as surface electrons and positrons, stripped from the thin atmosphere or created through magnetic processes, experience forces that human intuition cannot accommodate. The magnetic field near the poles reaches such intensity that these particles cannot move sideways. They can only travel along magnetic field lines, spiraling tightly around them at velocities approaching the speed of light. As these relativistic particles accelerate along curved field lines, they emit electromagnetic radiation. This radiation isn't scattered evenly in all directions. Instead, it concentrates into tight beams aligned with the magnetic poles beams that sweep through space like searchlights as the neutron star rotates. Dr. Duncan Lorimer at West Virginia University, who has discovered numerous pulsars, describes this as the cosmos's most powerful broadcasting system, transmitting on frequencies from radio waves through gamma rays. When one of these beams happens to sweep across Earth's direction, our telescopes register a pulse. When the beam rotates away, we see nothing. Then the beam returns, exactly on schedule, exactly as predicted, every single rotation. This is the mechanism producing pulsar signals. We aren't detecting the neutron star directly. We're catching glimpses of its magnetic searchlight as it spins past our line of sight. The radio waves we detect from pulsars represent only a tiny fraction of the energy being broadcast. These beams span the electromagnetic spectrum from radio frequencies through visible light to X-rays and gamma rays. The Crab pulsar, that remnant of the 1054 supernova, has been photographed flashing in visible light appearing and disappearing 30 times per second, visible through sufficiently sensitive cameras. The same object flashes in X-rays. The same object flashes in gamma rays with energies millions of times greater than visible light. What determines the precise characteristics of these pulses? Several factors converge. The width of each pulse, how long the beam illuminates, US during each rotation, depends on the beam's opening angle and the geometry between the magnetic axis, spin axis, and our line of sight. Narrower beams produce sharper pulses. The intensity depends on the particle population accelerating along field lines and the magnetic field strength driving the acceleration. But the timing, that extraordinary, atomic clock rivaling precision, stems from something more fundamental. It comes from the rotational stability of the neutron star itself. Consider what might perturb a rotating object. External torques could slow it or speed it up. Internal structural changes could alter the moment of inertia, affecting rotation rate. Friction with surrounding material could drain angular momentum. Gravitational interactions with nearby objects could introduce wobbles or variations. Neutron stars experience essentially none of these perturbations. They exist in the vacuum of space, typically isolated from significant gravitational influences. Their surfaces are among the most rigid structures in the universe, crystalline ion lattice, bound together by stupendous gravity and degenerate neutron pressure. Their interiors may contain exotic superfluid and superconducting phases that conduct rotational motion with essentially zero friction. Dr. Jim Latimer at Stony Brook University has calculated that the effective shear modulus of a neutron star crust exceeds that of any known material by factors of billions. Diamond shatters under stresses that a neutron star crust wouldn't notice. This rigidity means the star cannot deform appreciably, cannot oscillate, cannot experience the internal variations that would produce timing irregularities. The result is rotational stability beyond anything else in nature. The fastest known millisecond pulsars maintain their rotation periods to 14 decimal places when observed over years. This means that after spinning over 20 billion times, the cumulative timing error might be a few millionths of a second. Your heartbeat varies by larger percentages between adjacent beats. But here's where observers encounter something initially puzzling. Pulsars don't maintain their spin rates forever. They slow down gradually, predictably, but measurably. A pulsar spinning at 10 rotations per second might slow to 9.999 rotations per second over a few hundred years. This spin down occurs because the rotating magnetic field acts as a brake. As the magnetic field sweeps through space, it generates electromagnetic radiation, carrying energy away from the system. Energy loss means rotational energy loss. Rotational energy loss means the spin rate decreases. This isn't a timing instability. It's a predictable, modelable effect that astronomers incorporate into their observations. Once you account for the spin-down rate, the underlying timing precision remains astonishing. The relationship between spin-down and magnetic field strength gives astronomers a tool for measuring pulsar properties. Strong magnetic fields produce rapid spin-down. Weak magnetic fields produce slow spin-down. Millisecond pulsars, which spin fastest but slow down most gradually, possess relatively weak magnetic fields, a consequence of their unusual formation history, which we'll explore later. One remarkable confirmation of the lighthouse model came from studying the Crab pulsar in detail. Astronomers know this pulsar's age precisely. It's been spinning since that supernova in 1054 CE. By measuring its current spin rate and spin-down rate, they can calculate how fast it should have been spinning at birth. Working backward from the spin-down equations predicts an initial rotation period of approximately 16 milliseconds. This matches theoretical expectations for newly formed neutron stars. The physics is internally consistent. More dramatically, the Crab pulsar's spin-down energy exactly accounts for the luminosity of the surrounding nebula. The rotational energy being lost by the pulsar, approximately 5 million trillion watts, reappears as the glow of the Crab nebula. The pulsar is literally powering its own cosmic showcase, converting rotational energy into the electromagnetic radiation that makes the nebula visible across 50,000 years of expansion. You might wonder why we don't see all neutron stars as pulsars. The answer lies in geometry. If the magnetic beam never sweeps across Earth's direction, if we happen to view the pulsar from an angle perpendicular to the beam's path, we detect nothing. Estimates suggest we see roughly 1 in 5 neutron stars as pulsars, simply because of favorable geometry. Billions more spin silently, their beams sweeping empty space, never touching our planet. Additionally, pulsars eventually spin down so much that their beams fade. Below certain rotation rates and magnetic field strengths, the particle acceleration mechanisms cannot function efficiently. The lighthouse turns off. These dead pulsars continue spinning, but without detectable emission. The graveyard of extinguished pulsars probably contains far more objects than the active population we observe. Yet within the population we can detect, the precision remains. That precision enables something extraordinary, the use of pulsars as cosmic laboratories for testing physics under conditions we cannot recreate on Earth. Before we examine those tests, we need to understand just how extreme the conditions within a pulsar truly are. The numbers will challenge your intuition at every step. Chapter 3. Extreme Physics. The interior of a neutron star represents the most extreme physical environment in the observable universe outside black holes. Every parameter describing conditions within these objects, temperature, density, pressure, magnetic field, exceeds terrestrial experience by factors that render comparison nearly meaningless. Yet understanding these extremes proves essential for grasping why pulsars behave as they do. Begin at the surface. A neutron star's outer crust consists of iron nuclei arranged in a crystalline lattice, crushed together by gravitational pressure. roughly 200 billion times greater than atmospheric pressure on Earth. This iron differs fundamentally from the iron in your blood or in structural steel. Atoms in normal matter are mostly empty space electron clouds surrounding tiny nuclei. But under neutron star surface conditions, electrons are compressed into regions thousands of times smaller than normal, producing metallic properties more extreme than any material we know. Descend deeper, and the physics grows stranger. Below roughly 1 kilometer, the pressure becomes so intense that iron nuclei themselves begin to merge and distort. Nuclear physicists call this the nuclear pasta zone, a region where matter adopts shapes resembling lasagna, spaghetti, and gnocchi. These aren't metaphors. They're actual descriptions used in technical papers. Dr. Charles Horowitz at Indiana University has calculated that nuclear pasta may be the strongest material in the universe, exceeding the breaking strain of steel by 10 billion times. Below the pasta layer, around several kilometers depth, you enter the outer core. Here, nuclei can no longer maintain separate identities. Matter dissolves into a continuous fluid of neutrons, roughly 95% neutrons, with a small admixture of protons and electrons required by charge balance. This neutron fluid behaves unlike any substance humans have ever encountered directly. At the temperatures and densities present in neutron star cores, the neutron fluid becomes superfluid. Normal superfluids like helium cool near absolute zero flow without friction, climb walls, and exhibit quantum mechanical properties at macroscopic scales. Neutron star superfluidity operates on these same principles, but at temperatures of millions of degrees rather than near absolute zero. The neutron fluid rotates not through conventional flow, but through quantized vortices, microscopic tubes of circulating matter distributed throughout the core. Similarly, the protons in the core likely become superconducting, a state where electrical current flows without resistance. This superconductivity affects how the magnetic field threads through the stellar interior, with implications we'll explore when discussing magnetic field evolution. But the deepest interior, the inner core, occupying perhaps the central few kilometers, remains genuinely unknown. Density there reaches approximately 5 to 10 times nuclear saturation density. These are conditions never achieved in any laboratory experiment. Particle accelerators produce similar densities, but only in minuscule volumes for tiny fractions of seconds. Neutron star cores maintain these densities permanently across several cubic kilometers. What exists at these densities? Nobody knows with certainty. Some theories propose that quarks, the fundamental constituents of protons and neutrons, become liberated from their usual confinement. Rather than being bound into nucleons, quarks might roam freely in a state called quark matter. Other theories suggest hyperons might form exotic particles containing strange quarks that are unstable under normal conditions, but potentially stable under these pressures. Still other proposals invoke kaon condensates or color superconducting phases. Dr. Faryal at the University of Arizona has spent years attempting to constrain neutron star interior composition through careful observations. Her measurements of neutron star masses and radii, combined with theoretical equations of state, gradually narrow the possibilities. But fundamental questions remain open. The interiors of neutron stars probe physics inaccessible by any other method. Now consider the magnetic field. We mentioned earlier that neutron star magnetic fields reach trillions of Gauss. For perspective, Earth's magnetic field measures roughly half a Gauss. The strongest sustained magnetic fields produced in laboratories reach perhaps 500,000 Gauss. Neutron star fields exceed this by factors of millions to billions. At field strengths above about 44 billion Gauss, a threshold called the quantum, critical field electromagnetic phenomena become dominated by quantum electrodynamics effects. Vacuum itself becomes magnetically birefringent, meaning light travels at different speeds depending on its polarization. Electron orbitals become highly elongated along field lines, making normal atomic structure impossible. Atoms become needle-shaped objects oriented along magnetic field directions. Some neutron stars called magnetars possess fields reaching 10 trillion to 100 trillion Gauss, or even higher. These are the most intensely magnetized objects known. Their fields are so strong that at the distance of the Moon, they would erase every credit card on Earth. At the distance of Mercury, they would distort the orbits of electrons in human tissue. At close range, they would simply tear matter apart through purely magnetic forces. For normal pulsars, typical fields measure between 100 million and 1 trillion Gauss. Still extreme by any terrestrial standard, but not quite reaching magnetar territory. These fields drive the particle acceleration producing the beams we observe. They also create the braking torque that gradually slows pulsar rotation. Temperature represents another extreme. Newly born neutron stars emerge from supernova at temperatures exceeding 100 billion degrees hotter than the cores of the most massive stars, hotter than conditions during Big Bang nucleosynthesis. These objects cool rapidly at first, primarily through neutrino emission from their interiors. Neutrinos pass through the solid crust essentially unimpeded, carrying away thermal energy directly from the core. Within about 100,000 years, surface temperatures drop to roughly 1 million degrees. This remains hot enough to produce significant X-ray emission. The NICER instrument on the International Space Station currently monitors several nearby pulsars and X-rays, tracking how thermal emission patterns change as they rotate. These observations reveal surface temperature variations, helping astronomers map neutron star surfaces with unprecedented resolution. The gravity at a neutron star surface deserves particular attention. With mass comparable to the Sun compressed into a 20-kilometer sphere, surface gravity reaches approximately 200 billion times Earth's gravity. You would be instantly crushed into a layer perhaps atoms thick. Light trying to escape the surface must climb out of such a deep gravitational well that it loses roughly 20% of its energy, gravitational redshift easily measurable from Earth. This intense gravity produces another effect essential for pulsar observations. Any slight deviation from perfect sphericity gets rapidly erased. Irregularities on a neutron star surface, mountains if you will, cannot exceed a few centimeters in height. The gravitational stress would simply crush anything taller. This enforced smoothness contributes to the rotational stability. There are no bumps, no asymmetries, nothing to create wobbles or irregular torques. Dr. Kostas Glampadakis at the University of Mercia has calculated that the maximum mountain on a neutron star, given the stiffest possible crustal material, might reach perhaps 10 centimeters. More realistic estimates suggest millimeter-scale irregularities. Compare this to Earth's mountains reaching kilometers high, and you glimpse how gravity smooths these objects into nearly perfect spheres. These extreme conditions, the superfluid cores, the overwhelming magnetic fields, the crushing gravity, the temperatures spanning from billions of degrees to mere millions, all combine to produce objects unlike anything else in the cosmos. They are neither stars nor planets nor anything familiar. They occupy their own category of existence, following physics that we can barely calculate and cannot possibly experience. Yet despite all this extremity, or perhaps because of it, they maintain timing precision that puts human technology to shame. The same conditions that make neutron stars incomprehensible also make them perfect. Understanding that perfection requires examining what happens over time, how these objects age and evolve while maintaining their clock-like reliability. Chapter 4: Millisecond Mastery Among the Thousands of Known Pulsars. A special population stands apart objects spinning so rapidly that their precision defies belief. These are the millisecond pulsars, rotating hundreds of times per second, their timing stability rivaling the most advanced atomic clocks ever constructed. They represent pulsar evolution's endpoint, and their existence tells a story of cosmic resurrection. Ordinary pulsars are born spinning fast but slow down continuously through magnetic braking. The Crab pulsar, roughly 1,000 years old, already rotates 30 times per second rather than the estimated 62 times per second it possessed at birth. Given enough time, millions of years, it will slow to perhaps one rotation every few seconds. Eventually, it will spin too slowly to power detectable emission. It will become electromagnetically dead. But some pulsars receive a second chance at life. Millisecond pulsars form through a process called recycling. When a neutron star exists in a binary system with a companion star, evolution can transfer matter from the companion onto the neutron star. As gas spirals inward, it carries angular momentum with it. This angular momentum gets deposited onto the neutron star, spinning it up. Over millions of years of steady accretion, an old, slowly rotating neutron star can be accelerated to millisecond rotation periods. The first millisecond pulsar, designated PSRB 1937+21, was discovered in 1982 by Donald Backer and colleagues at the Arecibo Observatory. Its period, 1.558 milliseconds, meant it was rotating 642 times per second. This exceeded the rotation rate of every known pulsar by more than an order of magnitude. Initial reactions ranged from disbelief to wonder. How could any object spin this fast without flying apart? The answer lies in neutron star compactness. Centrifugal forces at the equator of a rapidly spinning object try to fling material outward. For a neutron star to rotate at 642 times per second, the centrifugal acceleration at its equator approaches the gravitational acceleration holding matter in place. But gravity at a neutron star surface is so overwhelming that even these extreme centrifugal forces cannot overcome it. The object remains bound, spinning at rates that would disintegrate any normal star. Dr. Paulo Freire at the Max Planck Institute for Radio Astronomy has studied millisecond pulsars for decades. He notes that their timing precision stems partly from their weak magnetic fields. During the recycling process, accreted matter appears to bury or dissipate the strong magnetic fields that ordinary pulsars possess. Millisecond pulsars typically have fields of only about 100 million Gauss strong by terrestrial standards, but weak compared to ordinary pulsars. Weaker magnetic fields mean slower spin down. Where the Crab pulsar loses energy rapidly through magnetic braking, millisecond pulsars lose energy at a glacial pace. PS RJ 04374715, one of the closest and brightest millisecond pulsars, will require approximately 20 billion years to spin down appreciably far longer than the current age of the universe. For all practical purposes, it will spin at its current rate forever. This slow spin down contributes to timing stability. Any irregular variations in spin down rate would manifest as timing irregularities. But because millisecond pulsars spin down so slowly, these variations, if they exist, remain buried below measurement thresholds. The pulses arrive with metronomic regularity. How regular exactly? The most stable millisecond pulsars maintain timing residuals, the difference between predicted and observed pulse arrival times of less than 100 nanoseconds over decades. 100 nanoseconds is the time light travels roughly 30 meters. Across 10 years of observations, these pulsars arrive within 30 meters of their predicted positions, even though they're located thousands of light years away. This represents fractional stability of approximately 1 part in 10 quadrillion. For comparison, the best atomic clocks on Earth achieve stability of about 1 part in 10 to the 18th power over certain timescales. Millisecond pulsars approach this performance using nothing but neutron matter and magnetic fields. No laboratory, no cryogenics, no feedback systems. Just physics operating at extremity. The population of known millisecond pulsars now exceeds 400 objects. Most reside in binary systems, their companions being white dwarfs, the remnant cores of the stars that donated mass during the recycling phase. The companion star long ago exhausted its envelope, leaving only a cooling stellar ember orbiting the pulsar it helped create. Some millisecond pulsars exhibit fascinating phenomena in their binary orbits. PSRJ 0348 plus 0432, for example, orbits a white dwarf every 2.46 hours, one of the shortest known orbital periods for a pulsar binary. The intense gravitational interaction in this system produces measurable relativistic effects, providing tests of Einstein's general relativity in the strong field regime. Others exist in even more exotic configurations. PSRJ 0337 plus 1715 orbits within a triple system, with a white dwarf companion plus an outer white dwarf. This hierarchical triple provides unique opportunities to test gravitational theories, particularly whether all objects fall at the same rate regardless of their composition, the strong equivalence principle. Measurements have confirmed this principle to exquisite precision. The Fermi Gamma Ray Space Telescope has revealed that many millisecond pulsars produce pulsed gamma ray emission in addition to radio waves. This gamma ray population helps astronomers understand particle acceleration mechanisms operating in the pulsar magnetosphere. Different wavelengths probe different regions and processes, building a comprehensive picture of these extreme objects. One particularly strange category within millisecond pulsars involves the Black Widow and Redback systems. In these binaries, the pulsar wind, an outflow of energetic particles driven by the spinning magnetic field, ablates the companion star. The pulsar is literally destroying its partner, stripping away atmosphere and gradually consuming the star that gave it renewed life. Black Widow companions have been reduced to objects less massive than Jupiter, slowly evaporating under the relentless particle bombardment. Dr. Anne Archibald at the University of Amsterdam has studied these systems extensively. She notes that some transitional objects appear to switch between states, sometimes appearing as radio pulsars, sometimes as X-ray binaries actively accreting material. These transitions reveal the recycling process in action, catching pulsars in the act of spinning up. For timing applications, millisecond pulsars offer unparalleled performance. Pulsar timing arrays networks of precisely timed millisecond pulsars distributed across the sky function as galaxy-scale gravitational wave detectors. Any passing gravitational wave would alter the spacetime between Earth and the pulsars, producing correlated timing deviations. We'll explore this application in detail later, but it demonstrates how millisecond pulsar precision enables entirely new observational capabilities. The distribution of millisecond pulsars throughout the galaxy traces different evolutionary pathways than ordinary pulsars. While young pulsars concentrate in the galactic disk where star formation occurs, millisecond pulsars have had billions of years to migrate. Some have been flung to great heights above the disk by gravitational interactions. Others orbit in globular clusters, ancient spherical concentrations of stars where close encounters favor binary formation and mass transfer. The globular cluster Terzan 5 contains at least 40 known pulsars, most of them millisecond objects. The dense stellar environment creates binary systems at high rates, providing ample opportunities for recycling. Other clusters harbor similarly rich pulsar populations. These laboratories demonstrate how stellar dynamics influences pulsar formation and evolution. You might wonder whether there's a limit to how fast a pulsar can spin. Theoretical calculations suggest that rotation periods much below about half a millisecond would cause the neutron star to shed mass from its equator or possibly collapse to a black hole, depending on its internal structure. The fastest known pulsar, PSRJ 17482-446 at 716 rotations per second, approaches but does not reach this limit. Whether faster objects await discovery remains an open question. What makes millisecond pulsars truly remarkable isn't just their speed or their precision, it's their origin story. They are resurrected objects, dead stars brought back to electromagnetic life through cosmic mass transfer. They've been reborn as the universe's most accurate clocks, ticking away in the darkness, available for anyone with the right instruments to monitor. This precision has already enabled revolutionary discoveries, transforming our understanding of gravity itself. Chapter 5. Gravitational Proof. In 1974, Russell Hulse and Joseph Taylor pointed the Arecibo telescope at a newly discovered pulsar and noticed something remarkable. The pulsar's signal wasn't arriving at perfectly regular intervals. Instead, the timing shifted systematically faster at some times, slower at others, following a pattern that repeated every 7.75 hours. This wasn't a timing instability, it was Doppler shift. The pulsar was orbiting something. That something turned out to be another neutron star. PSR B1913+16, now called the Hulse-Taylor binary, became the first double neutron star system ever discovered. Its importance for fundamental physics cannot be overstated. This single system provided the first strong field test of Einstein's general relativity and the first evidence for gravitational waves decades before LIGO's direct detection. The orbit of the Hulse-Taylor binary is extreme by any standard. Two neutron stars, each containing roughly 1.4 solar masses, orbit their common center of mass in under 8 hours. Their closest approach brings them within about 1 solar radius of each other, close enough that relativistic effects become substantial. Their maximum separation exceeds 3 solar radii. The orbital velocity at closest approach exceeds 1,000th of the speed of light. Under these conditions, general relativity predicts effects invisible in weaker gravitational fields. The orbit should precess, as its orientation in space should rotate over time. Newtonian gravity predicts no such precession for an isolated two-body system. Mercury's orbital precession, which helped confirm general relativity in 1915, amounts to 43 arcseconds per century. The Hulse-Taylor binary's orbit precesses by 4.2 degrees per year, more than 35,000 times faster. Timing measurements of the pulsar confirm this precession with extraordinary precision. The orbit rotates exactly as Einstein's equations predict. This wasn't a marginal confirmation with large uncertainties. It was exact agreement to within measurement error, which by now spans less than 0.04% of the predicted value. But the most profound prediction concerned gravitational waves. General relativity states that accelerating masses produce ripples in spacetime that propagate outward at the speed of light, carrying energy away from the source. Two neutron stars in close orbit, whipping around each other every few hours, should radiate substantial gravitational wave energy. This energy loss must come from somewhere from the orbital energy of the system itself. As the binary loses energy to gravitational radiation, the two neutron stars should spiral closer together. Their orbital period should decrease. General relativity provides exact predictions for how quickly this spiral should proceed. For the Hulse-Taylor binary, the orbit should shrink such that the orbital period decreases by about 76 microseconds per year. Taylor and collaborators monitored this system for years, then decades. By 1979, they had accumulated enough timing data to measure the orbital decay rate directly. It matched Einstein's prediction. By 1993, when Taylor and Hulse received the Nobel Prize in Physics, the agreement had reached 0.2%. Today, after nearly 50 years of observation, the agreement has improved to better than 0.2%, with the minuscule remaining difference likely attributable to subtle effects like galactic acceleration. Dr. Ingrid Stairs of the University of British Columbia has worked on binary pulsar timing for over 2 decades. She describes the Hulse-Taylor system as general relativity's crowning confirmation, a test conducted not in weak fields near Earth, but in the intense gravitational environment near neutron stars, precisely where deviations from Einstein's theory might appear if they existed. Additional relativistic effects appear in pulsar timing. Gravitational redshift alters pulse arrival times as the pulsar moves between different gravitational potential depths during its orbit. The Shapiro delay extra travel time for signals passing through curved spacetime near the companion produces distinctive signatures when orbital geometry allows. Time dilation, affecting the pulsar's proper time relative to our observation frame, creates predictable timing variations. Each of these effects provides an independent test of general relativity. Each must be present simultaneously, with consistent values for system parameters like masses and orbital elements. Pulsar timing achieves such precision that discrepancies at even the parts per million level would be detectable. None appear. General relativity passes every test. Since the Hulse-Taylor binary, astronomers have discovered additional double neutron star systems, each providing new testing grounds. PSRJ 07373-039, discovered in 2003, proved especially valuable. It's the only system where both neutron stars are visible as pulsars. This double pulsar allows measurements of relativistic effects from both objects, providing even more constraints on gravitational theory. The double pulsar's orbital period is even shorter than Hulse-Taylor's 2.4 hours. At closest approach, the two pulsars are separated by less than 3 Earth-Sun distances. Under these conditions, relativistic effects reach extreme magnitudes. Orbital precession exceeds 16 degrees per year. The measured orbital decay rate confirms gravitational wave emission at the 0.05% level, the most precise strong field test of general relativity ever performed. Michael Kramer at the Max Planck Institute for Radio Astronomy, who co-discovered the double pulsar, has noted that these systems test aspects of gravity theory inaccessible by any other means. Gravitational wave detectors like LIGO observe merging compact objects during their final moments. Pulsar timing observes long before merger, tracking decades of orbital evolution with sustained precision. The upcoming Square Kilometre Array, a massive radio telescope under construction across Australia and South Africa, will discover thousands of new pulsars. Among these should be systems even more extreme than currently known. Perhaps a pulsar orbiting a black hole, the ultimate strong field laboratory. Such a system would probe spacetime near the black hole event horizon, testing aspects of general relativity never before accessible. Beyond testing Einstein's theory, pulsar timing addresses alternatives. Some modified gravity theories propose to explain dark matter or dark energy without these substances, make predictions differing subtly from general relativity. Pulsar timing systems can distinguish between these predictions. To date, no deviation from Einstein's predictions has been found. This doesn't prove general relativity correct. Absolutely, science never proves anything absolutely, but it eliminates wide swaths of alternative theories. The gravitational wave aspect deserves special emphasis. For decades after Einstein proposed gravitational waves in 1916, many physicists doubted they were real physical phenomena rather than mathematical artifacts. The Hulse-Taylor binary's orbital decay provided indirect but utterly convincing evidence. The orbit is shrinking. The energy is going somewhere. Gravitational waves are the only known destination. This indirect detection preceded LIGO's direct detection by more than 40 years. When LIGO finally observed gravitational waves from merging black holes in 2015, the result confirmed what pulsar astronomers had known since the 1970s. Gravitational waves are real. They carry energy. They affect the sources that emit them exactly as general relativity predicts. You might wonder why pulsar timing achieves such exquisite gravitational tests. The answer combines several factors. Pulsars provide extraordinarily stable reference clocks. Their orbital motions are clean, no atmospheric drag, no tidal distortions, just two compact objects obeying gravitational dynamics. Observations can continue for decades, accumulating millions of pulse arrival times. And the systems themselves inhabit the strong field regime, where deviations from general relativity would most likely manifest. The combination proves powerful beyond any single factor. A less stable clock wouldn't permit precise relativistic measurements. A system in weaker gravitational fields wouldn't exhibit measurable effects. Short-duration observations couldn't average down timing noise. Pulsar binaries uniquely combine stability, field strength, and observational duration. These gravitational conformations represent perhaps the most profound scientific application of pulsar precision. They've transformed general relativity from a theory tested mainly in weak fields to one verified under the most extreme gravitational conditions nature provides. But the applications extend further still. Pulsars don't just test gravity. They're now being used to detect gravitational waves from entirely different sources, turning the cosmos itself into a detector. Chapter 6. Cosmic Detector. In June 2023, multiple pulsar timing collaborations around the world simultaneously announced evidence for a gravitational wave background permeating the universe. ANANOGREV in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array had each independently found the same signal. After decades of searching, a new window on the gravitational universe had finally opened, built entirely on pulsar precision. The concept behind pulsar timing arrays represents audacious scientific engineering. Rather than building a single gravitational wave detector, astronomers used the galaxy itself as an instrument. Millisecond pulsars scattered across the sky serve as reference beacons. Gravitational waves passing between Earth and these pulsars stretch and compress the intervening spacetime, altering pulse arrival times in characteristic patterns. Here's how it works. A gravitational wave is a ripple in spacetime itself, a distortion that alternately stretches space in one direction while compressing it in the perpendicular direction. As such a wave passes between Earth and a pulsar, the distance between them fluctuates. This fluctuation appears as a variation in pulse arrival times, pulses arriving slightly early when the distance shrinks, slightly late when it expands. A single pulsar-Earth pair cannot distinguish gravitational waves from other timing effects. Perhaps the pulsar has intrinsic instabilities, or perhaps local clock errors contaminate the data. But gravitational waves produce correlated signals across multiple pulsars. A wave washing over the galaxy will affect different pulsar-Earth pairs in predictable, geometry-dependent ways. By analyzing timing residuals from dozens of millisecond pulsars simultaneously, astronomers can extract gravitational wave signals from the noise. The required precision is staggering. Gravitational waves from sources detectable by pulsar timing arrays, primarily supermassive black hole binaries in distant galaxies, produce timing variations of perhaps 100 nanoseconds over observation spans of years to decades. Detecting such signals requires timing stability better than this, maintained across multiple pulsars for multiple decades. Only millisecond pulsars provide adequate performance. Dr. Stephen Taylor at Vanderbilt University, a key figure in ANANOGREV's gravitational wave search, describes the challenge as measuring the width of a human hair from 10 kilometers away, then doing it again and again for 20 years. The collaborative effort involves dozens of radio telescopes, hundreds of researchers, and petabytes of timing data accumulated since the 1990s. The signal announced in 2023 differs from the gravitational waves detected by LIGO and Virgo. Those ground-based detectors observe high-frequency waves from merging stellar mass black holes and neutron stars, events lasting seconds with frequencies of tens to thousands of hertz. Pulsar timing arrays observe ultra-low frequency waves with periods of years to decades billion times lower frequency than LIGO's domain. What produces waves at these frequencies? The leading candidates are supermassive black hole binaries, pairs of black holes containing millions to billions of solar masses, orbiting each other at the centers of merging galaxies. When galaxies collide, their central black holes eventually sink toward the merged center through dynamical friction, form binary systems, and spiral together over millions of years. During this spiral, they emit gravitational waves that, collectively, create a random gravitational wave background filling the universe. The signal detected represents not individual binary merges, but the superposition of countless binaries throughout cosmic history. It's a stochastic background, a kind of gravitational wave pervading spacetime. Its detection confirms predictions about galaxy merger rates and supermassive black hole populations while opening entirely new research directions. Dr. Chiara Mingarelli at Yale University has modeled how individual binaries might eventually emerge from this background. As observations continue and timing precision improves, astronomers expect to resolve discrete sources-specific supermassive black hole binaries in nearby galaxies. These detections would enable studies of black hole demographics, galaxy evolution, and a final parsec problem, the long-standing puzzle of how black hole binaries complete their merger after dynamical friction becomes ineffective. The infrastructure supporting pulsar timing arrays spans the globe. ANEA Nogreve primarily uses the Green Bank Telescope in West Virginia and, before its collapse in 2020, the Arecibo Observatory in Puerto Rico. The European array employs 5 major telescopes across the continent. The Australian collaboration centers on the Parkes Telescope, while China uses the 500-meter aperture spherical telescope, the world's largest single-dish radio telescope. This international cooperation extends beyond sharing results. The International Pulsar Timing Array Consortium coordinates efforts, combines datasets, and develops analysis techniques applicable worldwide. Gravitational wave detection through pulsar timing is inherently a global endeavor. Looking forward, the square-kilometer array will transform pulsar timing capabilities. Its unprecedented sensitivity will discover thousands of new millisecond pulsars, many suitable for timing array inclusion. More pulsars mean better sky coverage, improved signal detection, and the ability to localize gravitational wave sources rather than just detecting their presence. The array might also detect gravitational waves from more exotic sources. Cosmic strings theoretical defects in spacetime that might have formed in the early universe would produce distinctive gravitational wave signatures. Phase transitions in the early universe, inflationary gravitational waves, and other cosmological phenomena could leave imprints detectable by sufficiently sensitive pulsar timing arrays. This transforms pulsars from objects of study into instruments of study. Their precision becomes a tool for investigating phenomena completely unrelated to neutron star physics. They're cosmic sensors, their steady beats serving as references against which we measure spacetime itself. The philosophical implications deserve reflection. When you observe a pulsar, you're receiving signals from an object that has been broadcasting for millions or billions of years. That signal has crossed vast cosmic distances, passing through intergalactic space, potentially traversing gravitational wave backgrounds and cosmic magnetic fields. By the time it reaches your telescope, it carries information not just about the pulsar, but about everything the signal encountered en route. Pulsar timing exploits this. The pulse is a probe. Anything affecting the pulse's journey, gravitational waves, interstellar medium variations, planetary positions, even Earth's atmosphere, leaves an imprint. Teasing apart these effects requires sophisticated modeling, but the result is information about the universe encoded in timing data. You might ask whether this represents the ultimate application of pulsar precision. Perhaps not. Some researchers have proposed using pulsar timing for interstellar navigation. A spacecraft far from Earth, unable to receive GPS signals, could triangulate its position using pulsar signals. The X-ray timing of several pulsars, combined with their known positions and periods, would enable autonomous navigation across the solar system and beyond. NASA's Station Explorer for X-ray Timing and Navigation Technology, Sextant, demonstrated this concept using the NICER instrument on the International Space Station. It successfully determined the station's position to within 5 kilometers using pulsar timing alone, a proof of concept for future deep space applications. Imagine a probe heading to Alpha Centauri, 4 light-years distant. GPS satellites would be invisible. Ground-based tracking would suffer from light-speed delays. But pulsars would remain visible, their signals arriving from the same directions, with the same timing characteristics, regardless of the spacecraft's position. The dead stars would guide the living toward new worlds. This vision remains futuristic but technologically plausible. The precision is already available. The pulsars are already broadcasting. We need only develop the receivers and algorithms to utilize what the universe freely provides. From gravitational wave detection to interstellar navigation, pulsar applications continue expanding. Each application exploits the same fundamental property, timing stability, beyond anything humans have engineered. But this raises the question we've circled throughout this exploration. Why is that precision possible? What physical principles ensure that chaos produces clocks? Chapter 7. Stability Secrets. We've established that pulsars keep time with extraordinary precision. We've explored the applications this precision enables. Now we must confront the deeper question. Why does nature produce such stability from such violent origins? What physical principles guarantee that stellar explosions yield perfect clocks? The answer lies in the confluence of several factors, each insufficient alone but collectively ensuring reliability that rivals atomic standards. Understanding these factors reveals something profound about how the universe operates, about how extremity breeds perfection. Begin with angular momentum conservation. This principle, fundamental to physics, states that rotational motion persists unchanged unless external torques act. A figure skater spins faster when pulling in their arms because no external force changes their angular momentum. It must be conserved. Similarly, a collapsing stellar core spins up dramatically as its radius shrinks, and that spin persists essentially forever in the absence of external braking. Neutron stars exist in near-perfect isolation. The interstellar medium sparse gas and dust between stars is too thin to provide significant friction. Most neutron stars have no binary companions to gravitationally perturb their rotation. Even those in binary systems experience torques mainly through electromagnetic interaction with accreted material, not gravitational disturbance of their spin. The magnetic braking we discussed earlier provides the primary spin-down mechanism, but it operates predictably. The torque depends on magnetic field strength, rotation rate, and field geometry, all stable properties for a given neutron star. This allows astronomers to model spin-down precisely, accounting for it in timing solutions. What remains after subtracting the systematic spin-down is phenomenal stability. Next, consider structural rigidity. A neutron star's crust, composed of crystalline nuclear material bound by extreme gravity, resists deformation with adamantine stubbornness. Any irregularity, any bump, any mountain, any asymmetry would cause the rotation axis to wobble or would emit additional gravitational waves, draining rotational energy. But the crushing surface gravity prevents such irregularities from forming or persisting. Dr. Nils Anderson at the University of Southampton has calculated crustal elasticity under neutron star conditions. His results indicate breaking strains roughly 10 billion times greater than steel. This material doesn't flex. It doesn't flow. It maintains its shape essentially forever under gravitational compression. The interior superfluid and superconducting components contribute differently. Superfluids rotate through quantized vortices rather than continuous flow, and these vortices are pinned to the crystal lattice of the crust. This creates coupling between the fluid core and the solid exterior, transmitting rotational information with minimal dissipation. The entire star rotates as a unit, not as separate layers slipping past each other. Occasionally, this coupling breaks down suddenly, producing phenomena called glitches, abrupt speed-ups in pulsar rotation. The Vela pulsar experiences glitches roughly every 3 years, suddenly spinning about 1 part in a million faster before gradually recovering. These glitches are thought to result from vortices suddenly unpinning and redistributing angular momentum from the faster-spinning superfluid core to the slightly slower crust. Glitches demonstrate that the interior is not completely simple, but they're predictable in a statistical sense and don't compromise long-term timing. After glitch recovery, the pulsar returns to its stable behavior. For millisecond pulsars, glitches are rare to non-existent, perhaps because their weaker magnetic fields and slower spin-down create less stress between components. Temperature stability contributes another factor. While neutron stars cool dramatically in their first 100,000 years, thereafter their temperatures change extremely slowly. A neutron star 1 million years old has roughly the same thermal structure as one 2 million years old. This thermal stability prevents structural changes that might affect rotation. Consider by contrast an ordinary star, where convection churns material continuously, fusion rates fluctuate, and magnetic fields reverse on decade timescales. Such an object could never serve as a precision clock. Its internal chaos would manifest as timing noise. Neutron stars, thermally frozen and structurally static, avoid such chaos entirely. The absence of atmosphere or weather patterns matters similarly. Earth's rotation varies by milliseconds due to atmospheric angular momentum exchanges, oceanic currents, and core mantle coupling. Neutron stars have none of these complications. Their atmosphere, if they have one, is centimeters thick and gravitationally bound so tightly it can influence rotation. Gravitational quadrupole radiation provides another stabilizing influence. Any rotating object with asymmetric mass distribution emits gravitational waves, draining rotational energy. For neutron stars with their enforced sphericity, this emission is negligible. The mountains that don't exist can't radiate. The rotation persists undiminished by gravitational wave losses, except in extreme cases. Dr. Benjamin Owen at Texas Tech University has searched for continuous gravitational wave emission from spinning neutron stars using LIGO data. No detections have occurred, setting upper limits on neutron star asymmetry. These limits confirm theoretical expectations. Neutron stars are extraordinarily smooth, their gravitational wave emission too weak to detect with current instruments. Magnetic field stability deserves mention as well. While young pulsars have strong fields that evolve over millennia, older pulsars, including all millisecond pulsars, have relatively stable magnetic configurations. Field evolution would alter spin-down rates, manifesting as timing irregularities. The observed stability implies field stability. The superconducting proton component in the core may play a role here. Superconductors expel magnetic fields through the Meissner effect, but in neutron stars, the field threads through quantized flux tubes rather than being expelled entirely. These flux tubes interact with crustal structure in complex ways, but the overall configuration can remain stable over astronomical timescales. What emerges from all these factors is a system designed by physics for stability. Every property that might introduce variability is either absent, suppressed, or made predictable. The neutron star becomes, in essence, a passive rotator, an object that simply maintains its spin because nothing significant disturbs it. This passivity contrasts with active timing references like atomic clocks. Atomic clocks achieve precision through feedback systems that lock oscillator frequencies to atomic transitions. They require power, maintenance, and environmental control. Neutron stars require nothing. They simply spin. The universe provides free, maintenance-free, eternally stable reference clocks distributed throughout the galaxy. There's something philosophically striking about this arrangement. The cosmos's most violent events, supernova explosions, produce the cosmos's most stable objects. Destruction breeds perfection. Chaos yields order. The very extremity that makes neutron stars incomprehensible also makes them reliable beyond measure. You might view this as evidence of fine-tuning, or you might see it as inevitable given physical law. Either interpretation acknowledges the remarkable outcome. From nuclear fires and gravitational apocalypse emerge timekeepers that will still be ticking long after Earth has been consumed by the Sun's expansion, long after our galaxy has merged with Andromeda, long after the last stars have burned out. These considerations lead naturally to questions of perspective and meaning. We've examined how pulsars work and why they maintain precision. But what do they mean? What does their existence tell us about the universe we inhabit and our place within it? These questions cannot be answered scientifically, but they deserve contemplation nonetheless. Chapter 8. Living Laboratory. The cosmic precision we've discovered isn't merely fascinating to contemplate. It has transformed our understanding of physics itself, turning pulsars into the most powerful laboratories in the universe, ones that let us test theories we could never examine on Earth. Consider what these spinning lighthouses allow us to probe. Every aspect of extreme physics that remains inaccessible to terrestrial experiments becomes suddenly testable when we point our telescopes at these remarkable objects. The laboratory stretches across light years, and the experiments run continuously, requiring only our attention to yield their secrets. Einstein's general theory of relativity makes predictions that become increasingly difficult to verify under normal conditions. The warping of space-time, the slowing of time in gravitational fields, the emission of gravitational waves, these phenomena require extreme environments to manifest measurably. On Earth, we can detect them only with the most sensitive instruments ever built. But pulsars provide natural laboratories where relativistic effects dominate the physics. The binary pulsar discovered by Hulse and Taylor in 1974 offered the first opportunity to test general relativity in the strong field regime. PSRB 1913 plus 16 consists of two neutron stars orbiting each other with a period of just 7.75 hours. The system's extreme gravitational field creates conditions Einstein could only imagine when formulating his equations a century ago. According to general relativity, two massive objects orbiting each other should emit gravitational waves ripples in the fabric of spacetime that carry energy away from the system. This energy loss should cause the orbit to shrink, bringing the stars progressively closer together. The orbital period should decrease at a specific rate calculable from Einstein's equations. For over 4 decades, astronomers have measured the orbital decay of this system. The pulsar's precision timing allows orbital parameters to be determined with extraordinary accuracy. The observed rate of orbital decay matches Einstein's prediction to within 0.2%, one of the most precise confirmations of general relativity ever achieved. This measurement provided the first indirect evidence for gravitational waves, decades before LIGO's direct detection. But the tests don't stop there. General relativity predicts multiple effects in strong gravitational fields, and binary pulsars allow scientists to measure them simultaneously. The advance of periastron, the rotation of the orbital ellipse, proceeds at about 4.2 degrees per year in the Hulse-Taylor system. Compare this to Mercury's periastron advance of just 43 arcseconds per century, which was itself considered a triumph of relativistic prediction. Time dilation effects appear prominently in these systems. As the pulsar swings through its elliptical orbit, its clock runs at different rates depending on its speed and its depth in the companion's gravitational well. These variations are measurable in the pulse arrival times, providing direct confirmation that time itself flows at different rates in different gravitational and kinematic conditions. The Shapiro delay offers another testable prediction. Pulses passing near the companion star take slightly longer to reach Earth because they must traverse curved spacetime. This delay amounts to mere microseconds, yet pulsar timing precision easily resolves it. The measured delays match relativistic predictions precisely, confirming that spacetime curvature affects light propagation exactly as Einstein described. In 2003, astronomers discovered an even more remarkable system. PSRJ 073-73039 became the first double pulsar, a binary, where both neutron stars emit detectable radio pulses. This cosmic gift provides unprecedented testing opportunities. With both stars visible as pulsars, scientists can measure orbital parameters from two independent perspectives, cross-checking relativistic predictions with redundancy never before possible. The double pulsar system has confirmed 5 distinct relativistic effects simultaneously, all agreeing with general relativity to high precision. No alternative theory of gravity has matched this comprehensive verification. Einstein's century-old equations, developed through pure thought experiments about elevators and trains, prove correct even under conditions he never could have conceived. Beyond testing Einstein, pulsars probe physics at densities impossible to replicate on Earth. The matter at a neutron star's core exists in states we cannot create in any laboratory. Particle accelerators achieve high energies, but cannot compress matter to nuclear density and beyond. The equation of state describing this ultra-dense material remains one of physics' profound mysteries. Pulsar observations constrain this equation of state through multiple channels. The maximum mass a neutron star can support before collapsing into a black hole depends on the properties of matter at extreme density. Measured pulsar masses therefore reveal information about nuclear physics at scales terrestrial experiments cannot access. In 2019, the NICER telescope aboard the International Space Station began measuring X-ray emissions from nearby pulsars with unprecedented precision. These observations determined neutron star radii to within a few hundred meters. Remarkable accuracy for objects thousands of light years distant. Combined with mass measurements, radius determinations constrain the relationship between pressure and density deep inside these stars. The results surprise physicists. Neutron stars appear slightly larger than many theoretical models predicted, suggesting that ultra-dense matter is stiffer than expected, that it resists compression more strongly than nuclear physics calculations indicated. This finding influences our understanding of all nuclear matter, not just the exotic states in neutron star cores. Pulsars also test the fundamental constants of nature. Some theories suggest that constants like the fine structure constant or the gravitational constant might vary over cosmic time or across different gravitational environments. Pulsar timing can detect such variations because changes in fundamental constants would alter pulse periods in characteristic ways. Decades of precision timing have found no evidence for varying constants, placing stringent limits on alternative theories. The universe appears to operate according to the same rules everywhere and everyone, a profound conclusion enabled by cosmic precision timing. Perhaps most remarkably, pulsars may someday detect gravitational waves directly through their timing signals. A background of gravitational radiation permeating the universe produced by merging supermassive black holes across cosmic history should create correlated timing variations in pulsars across the sky. The ANEA-NOGRAV collaboration and similar projects monitor dozens of millisecond pulsars precisely to search for this cosmic background. In 2023, these pulsar timing arrays announced evidence for such a background gravitational waves with periods of years to decades, far longer than what LIGO can detect. If confirmed, This discovery opens an entirely new window on the gravitational wave universe, accessible only because pulsars provide clocks stable enough to detect space-time ripples spanning decades. These objects that began as theoretical curiosities have become essential tools for fundamental physics. Their precision makes them irreplaceable laboratories for testing theories that would otherwise remain purely mathematical constructs. Each rotation, measured across interstellar distances, contributes data to humanity's deepest questions about the nature of space, time, and matter. The universe, it seems, has provided us with precisely the instruments we need to understand it, if only we have the wisdom to listen carefully to what they're retelling us.